Okay, we're going to dive in and have this additional examples of Bayes' rule to continue on with lesson 4. We'll go through these probably pretty quickly. You've hopefully already become familiar with Bayes' rule, and we're going to look at three different examples, and then one that I'm going to get started for you and leave you with to work on for practice. Okay, so here we go. Here's a kind of an interesting situation. We're going to try to decide whether or not to go to the beach this coming Saturday, and your decision is dependent on whether it's going to be sunny or rainy. So if the chances are that it's sunny, you're going to go, and if it's rainy, you're going to stay home. So what we know is, as of today, as report, there's an 80% chance of sun on Friday. And what we also know is that the local weather forecaster publicizes that they have a 95% accuracy on forecasts. So in other words, given from all of the days that are sunny, the forecast is correctly predicted that 95% of the time, or as the days that it's raining has predicted rain 95% of the time. So the first question that we want to answer is, with all of this information, what's the probability that the forecaster will predict sunshine? And if the forecaster predicts sunshine for Saturday, given that, what is the actual probability? Given that the forecaster predicts rain, what's the chance that it will actually rain? And then finally, if the forecaster predicts sunshine, of course, you want to know what you want to do. So our first step is to develop those events that are associated with this information. So let's just say, right, we're going to say that as some of our other examples, we've got 4 different possibilities. First of all, the weather can actually be sunny. We're going to say use the word sun to indicate that the weather is sunny. We're going to use rain, just the word rain, to indicate that the weather is rainy. So those, and then we have forecast. And somebody use quotes. When you see the quotes, it means forecaster predicts sunshine. And similarly, in quotes, rain, that's going to indicate that the forecaster predicts rain. So those are our 4 events. And the other thing that we can learn from this information is that we can begin to assign probabilities. So we know from earlier work that there's an 80% chance of sunshine. So our prior probability is that the probability, rather than writing this, we'll know that the probability of is 0.8. And by deduction, the probability that there's actually rain on Saturday is 1 minus, it's the complement of that, because there's only one other event, and it has to be either sunny or rainy. There's no hail, there's no tornado or hurricane. There's only one of 2 outcomes. So this probability has to be 0.2. And our other probabilities, what we know about the accuracy is as follows. So in the chance, in those times when the days it has been sunny, the forecast has been sunny 95% of the time. So given it's sun, the forecast has been correct 95% of the time. Similarly, the probability that rain is forecast of those days that it has actually rained has been correct. It's been a correct forecast 95% of the time. And so alternatively, the other events, even though those days have been sunny, the forecaster would have predicted rain. Even on those days when it's sunny, when it was sunny, there is a 5% chance that the forecast is incorrect. And similarly, on those days when it's actually rained, the forecaster has predicted sunshine even when it's rained 5% of the time. So this is all of the information that we have that's given to us from the outset. And again, what I want to make sure that you understand is clearly these are our prior probabilities. These are our conditional probabilities. And in this case, these two events are complement, but over here, these sets of two events where the condition describes indicates the fact that these are complementary events. It's based on this condition, not on the forecast that makes those complementary events. So given all of this information, now we're ready to go ahead and construct our decision tree. And the next one is what this decision tree looks like. Again, 80% of the days it's sunny, and then of 95% of those days the forecast was sunny. Given that the day was sunny, 5% it was rainy. And so 76% of the time the forecast was for sun and the day was sun, so on and so forth. In the other case, the other branch, there's a 20% chance of rain, but the forecast predicted sun 5% of the time, but correctly predicted rain 95% of the time. And doing the multiplications through this decision tree, this results in these joint probabilities. So the first question that we wanted to answer is what's the probability that sun was actually forecast? And if you think about this carefully, sun is forecast twice at the end of this tree. It's forecast correctly here, not correct, but it's forecast incorrectly here, but that is in fact the forecast. And so in 0.77, 77% of the time the forecast was for sun. And in this case, the forecast was rain. In this case, the forecast was rain. And so 0.4, 0.19, and 23% of the time, the forecast was rain. And this is the probability of the forecast being rain. I'm going to abbreviate that. And in this case, this is the probability that the forecast, in other words, quotes, was for sunshine. And so now we're ready to begin to calculate. So the answer to our first question is, what's here? It's this. This is the answer to part A. That the chance of a forecast of sunshine is 77%. So now we've got, this is our new information, and so what we want to do for part B is, what's the probability that if the forecast is sun, given that the forecast is sun, what's the chance that it actually will be sunshine? So what we want to calculate here is the following. We want to calculate the probability that it's actually sunshine given that the forecast was sunshine. And applying our Bayes rule, it's going to be the probability of sunshine and sunshine, this is the numerator, divided by the probability that there's actually sunshine forecast, which is the denominator. And so what this is going to turn out to be, to calculate this, is 0.76 divided by 0.77. And so this turns out to be 0.99%. So given this information, and you see this forecast of sunshine increases the probability that there's going to be sunshine. This is the probability of there being sunshine without information. Or before the forecast, and compared to this is the probability of sunshine with information, with the info. So that forecast is going to help us decide what we're going to do, and we can continue this process and compute all of those probabilities for each branch of this decision tree. And so you'll notice here, I've not done the division. I've done a subtraction, because I know that these two events, because this is a probability, this probability and this probability has to add up to 1, just as they do at every other branch in our tree. And so when I calculate this branch at being 0.99, I know the probability that it'll be rainy, actually be rainy, given a forecast of sunshine, is only 1 in 100. And similarly, this is the answer to part C, which is the probability that it'll rain given that there's a forecast of rain, and that's 3%. And once again, this is the probability that there was going to be rain with no information. And this is the probability of rain with information, with a forecast of rain. And so this is why why information is valuable and why it's important to get the forecast. And so what's going to happen in terms of your decision is if the forecast is sunny, then you will want to go to the beach because there's a 99% chance that it'll be sunny. And if the forecast is for rain, you're probably going to stay home because that chance that it's actually going to rain is 83%. So that's, again, how we're going to use Bayes' rule and how you use the decision tree. Okay, so let's look at another quick example. And we're going back to our previous problem of the disease. And we've gone back to the original process where there's only 1 in 1,000 adults that have this disease. And our tests are the same, 99% of the time positive, 2% negative. And you'll remember last time what we learned was the probability that the person actually had the disease given a positive test. Do you remember what that was? In this case, it was just about 5%. There was just about a 5% chance. Well, that doesn't really, to be honest, that doesn't really help us that much. It's just that means there's a 95% chance that the person doesn't have the disease, even with a positive test. So what we're going to do is we're going to go back and validate that test by giving a second test. All right, this test has the same accuracy, but if the first result is negative, we're not going to have a second test. So now how are we going to proceed? And again, we're going to use a decision tree. And we've already built this decision tree, or not decision tree, excuse me, probability tree. And this is what we did at the beginning of the last, during the last lesson. And so now what happens is as follows. If in those cases when we have a positive result, which is at the end of this top branch here, and in the other case where we have a positive result, which is even though the person does not have the disease, there could be a positive result. So in this situation, at the end of this branch, we're going to have another test. And so that test could either be positive or negative. And similarly, that second test is either positive or negative. And what happens at the end of this branch? Well, what you need to ask yourself is what happens in this branch? The person has the disease, but there's a negative test. And in this case, there's no other test. So the tree ends at that case. And similarly, in this branch, this situation ends that there's no test at the end of this branch. And so again, once there's a negative, there's no other test. And so now we know for this situation, we're going to have these probabilities are going to be repeated. And this is the case where we have two positives. And then this branch represents, there's a positive test and a negative. And this, of course, branch, there's a negative test, so there's no test. In this case, there's a positive test and another positive test. In this branch, there's a positive test and then a negative. And in this case, the first test is negative, and so there's no second test. All right, so let's take a look at this and see what happens then. So we want to know, first of all, let me type this out. We want to know, the question is, what's the probability that the person has the disease given that there's a positive test followed by a positive test, which we don't know. That's something that we don't know. And so using Bayes' rule, our numerator is going to be the probability that the person has the disease, and I'm going to abbreviate, positive, and there's two positive followed by a positive. That's the numerator. And the denominator is just what's the probability that there are back-to-back positives. Well, hopefully you can see that the numerator, this value is the numerator. It's you have the disease and there's two positives. Well, the question you should have, oh shoot, shouldn't have erased that, but the question you should have in your mind is, what's the denominator? So let me rewrite this. It's the probability that there's a disease and positive divided by the probability that there's two back-to-back positives, positive. And again, this value is the numerator. So the question is, what's the denominator? Well, the denominator is just going to be the sum of these two cases, because here's the situation where we have two positives tests back to back. You can see it along that branch. And here's the situation where we have two positive tests. So the total value is the sum of those two. When we add those together, that comes out to be the probability of positive equals, and it's 0.00137797. And so that value then is the denominator. So when we do this calculation, we divide 0.009801 divided by 0.0137797. What we learn is this value equals 71%. And so this is much better than what we had previously, if you remember, with just one test positive of 5%. And you may want to ask yourself, well, if we get two positive, we don't have the disease. And hopefully you can see it would be if you get two positives, it would be this value divided by 0.13797, which is 29%. Okay. So, and you could go ahead and think about this and ask yourself various questions about what are the outcomes. For example, if you have negative, what's the probability if you have the second test is the negative that you have the disease, and so forth. So, so that's the information available from a second test and the improvement on the reliability of the test and the chance that you would actually have disease. All right, so let's look at one final example. We'll leave this with you. And this one is very different. I'll give you a minute to read this. It has to do with automobile manufacturing. The manufacturer is thinking about introducing a new automobile. There's three things that could happen when the automobile is introduced. The sales will either be high, moderate, or low. All right, and there's probabilities associated with them. But there's an option to have a research group do a survey to determine, to help fast whether or not there's going to be the sales will be high, medium, or low. All right, and the forecast will be either that there's only two results from the forecast. Either the forecast is the market will be favorable or unfavorable market. All right, in previous instances, when the new vehicles were high 90% of the time, the report was favorable. The report was favorable 70% of the time when the sales were moderate, and when sales were low, 20% of the time. All right. So here's our set of questions. And again, what's the chance that the survey will produce a finding that of favorable? Given a favorable market, what's the chance that the sales will be either high or moderate? If the survey indicates an unfavorable market, what's the chance that it will be low, and then what should we do? So what I'm going to do is I'm going to help you get this started, and then I'm going to leave you to find those answers and ask questions if you need to. And so in this case, again, we're going to define our variables. And in fact, we're going to let the letter H is the market results in high sales. We're going to let M be that there's result is moderate sales of the automobile. And then we're going to let L be the event that there are low sales of the automobile. We're going to let F represent that the market survey indicates favorable market. And we're going to let U represent market indicates unfavorable. Those are our events, and now we know we also can begin to indicate our probabilities. So from the statement, what's the probability of high sales? If you might remember from the previous slide, that was 0.2. The probability that there were moderate sales was 50%. Well, there was no indication of what the probability of low sales is, but by deduction, you should realize that this is going to be the complement of these two. These two are 0.7. There's 70% chance of either high or medium sales. So the only other possibility is low sales. And so this is going to be 1 minus 0.7 or 0.3, 30% chance of low sales. All right, then for the other information that we're given is only with respect to the favorability of the report. And we're given the probability that there's a favorable report given high sales in the past is 90%. In other words, that was relatively easy to predict. The probability that there was a favorable report given moderate was 0.70, not 79, 0.70. The probability of a favorable report given low sales was only 0.2. Right, and so from there you'd be able to again realize the probability of an unfavorable report given high sales, the probability of an unfavorable report given moderate sales, and then the probability of an unfavorable report given low sales. And again, these are going to, you'll be able to, again, these two are the complements of one another. These two are the complements of one another, and these two are the complements of one another. All right. And so now we're ready to build our decision tree given this information. So, and this is where I'll begin and leave this with you. But we have now a 3-part decision tree, because what we know from past, sales are either high, medium, or low. And if sales were high in the past, the report was either favorable given high sales or unfavorable given high sales. And in the case where there was moderate sales, the report was either favorable given moderate sales or unfavorable given moderate sales. And then similarly, there was the report came back favorable, but given low sales or unfavorable given low sales. And at this point, you should be able to calculate through and determine what we want to answer. So part A is for part A, what we want to determine probability of a favorable report. For question B, we want to find the probability that given a favorable report, there's either high sales or if given that there's a favorable report, there's moderate sales. And for question C, we want to determine the probability that there's low sales given unfavorable report. So those are the three values that we want to need you to determine and calculate based on all of that information. And now for a slightly more complicated probability tree. I'm going to leave this you to determine and work through. And if you have questions, I will, in fact, what I'm going to do actually, we'll go ahead. And so we know that this answer is going to be, this is going to be equal to 0.59. The second answer to part B is 0.898. The answer to part C is 0.41. Oh, sorry, that's not correct. The answer to part C is 0.585. So take a look at this, see if you can come up with those answers, and if not, I'll be happy to help. Just please let me know if you have questions.